Is there a typo in decryption of C and public key? What is the typo? So for the decryption, no, I think it is correct because you pass. Yeah, the secret key. Yeah, that's correct. So you pass the secret key. Okay. And yeah, the rest should be okay. Yeah, thanks for pointing this out. All right, so we gained something, and then it was interesting, right? We just like a small message padding, we fix a huge vulnerability on an encryption system. This is a very good lesson for you to learn. And then the good point is like this kind of padding is not only limited to RSA, it is a generic function. I just use decryption and encryption. But you can imagine that this could be also used in different crypto systems. If they are deterministic, you can turn them into a non-deterministic or randomized algorithm. I'm sorry, non-deterministic is different. To a randomized algorithm, you can turn a deterministic to a randomized algorithm using this padding idea. All right. So I think now we can discuss about something else. We have gained something, but also with the price of losing something else. Remember in the basic RSA, we said that we have a homomorphic property saying that in a basic RSA, we said that when we encrypt, let me call y1 equals to, okay, let me go with the C. C1 equals to M1 to the E mod N, and C2 equals to M2 to the E mod N. We said that we can do homomorphic, this encryption system has homomorphic property, meaning that if you compute C1 times C2 mod N is equivalent of M1 times M2 to the E mod N, right? Which is actually encryption of public key with the given public key of M1 times M2, right? That was the property that we get. And we said that we can do privacy preserving encryption system. So now that we add this padding, the question is that what about OAEP RSA? So in OAEP, we are doing a padding. So we take our message M1, we pad it to X1, and then we would encrypt it as C1, which is X1 to the E mod N. And then our message M2, we pad it to some X2. And then we compute C2 equals to X2 to the E mod N. And given that, now if we do C1 times C2, it is going to be X1 times X2 to the E mod N, right? And this is not going to be equals to the encryption of M1 times M2, right? And the reason for that, I think it is obvious that we are doing padding to the messages. We are XORing your message with some pseudo-random generation function. And of course, we would lose that nice property that we had for doing or homomorphic encryption. So, well, we gain something with the lose of something else. But the truth is, we won't always use RSA for this purpose of, privacy preserving computation. Most of the time, RSA on the internet is used for key sharing, and sending some secrets. And for those purposes, we would never interested to use homomorphic, properties for the crypto system. What is the most important thing for us is that it is not a deterministic, it is randomized, and also it is secure against CCA attack. You know, now that we gained this one, it's a good point to remember that you know, we lost one of the nice property of the RSA. And with this kind of padding, unfortunately, we can't do anything about it. So it is that property of RSA is gone. All right. So let's get to hash functions. We've been talking about hash functions formally and informally, and I think now we can start to discuss what is a hash function and what does it has to do to make it a cryptographic hash function. So generally speaking, a hash function is a function that takes an arbitrary input. The star means any number of 0 and 1s, no matter how long they want to be, and always shrink them down, then get this input and output some fixed length output. Over here, we show it with n bits. So we get arbitrary input and we output only n bits. For example, n is always set. N can be 128. N can be 160 bits, right? So that is what it is saying. So given this definition, so we are talking about a function that has a huge domain and then has a very small range comparing to that set. So this is a large set, and then this is a very small set. And then we take some input from domain, and then we this hash function, we map it to the range, right? And then the range is such a small. So it is obviously possible that a lot of messages, they map to the same output, right? So because our range is fixed and our domain is huge, so of course we should have a lot of messages that maybe some other message over here that it also map to the same value, right? So let's call this one M and this one M prime, right? There should be a lot of them out there. So what is make this hash function a cryptographic hash function? It needs to satisfy these requirements. So the first thing first, it says that it is occlusion resistant. It should be hard for you to find two messages that M1 is not equal to M prime, but their hash are equal. So mathematically saying, it should be easy. We are asking to find M and some M prime such that M is not equal to M prime, and also hash of M, but hash of M equals to hash of M prime. So you know, just like this example that I gave you over here, it should be hard for you to find any two pair of messages. You know, you're not restricting to anything. Just give me any two pair of message that would map to the same value with this hash function. It should be computationally infeasible for a hash candidate to be able to find this pair. If you can find these two pair in any polynomial time, then this hash function is definitely, it is going to be a hash function, but it is not a cryptographic hash function. That's what we are saying. We have to have these two requirements. So another one that we have is a second pre-image resistant. This is another thing that we are looking for. That is setting some M. It should be hard to find another M that their hash is equal. So that is like in writing down in another word, given M, right? And then we are asking you to find M prime such that, of course, M should not equal to M prime, and also hash of M, but hash of M should equal to hash of M prime, right? So that is what we are saying. For the first one, we let you to be free. I think it's easier to solve because we are not restricting you. We are saying find me any pair that they have the same hash function. But for the second one, we are restricting you. It's a little bit harder. So we are saying that we fix one of them. So given M, you have to find another pair for this guy, M, that, you know, we can pass this test. So it is very important for a cryptographic hash functions to have these two properties. We would use them for integrity check, for example. If you want to check the integrity of M, we only store the hash of M. We don't need to store M. If M is changing anyways, to M prime, then we can detect it with the hash of M. So let me give you an example like how this could be useful now, given that these properties. Let's go through some examples. So you will see that a lot of virus protection softwares, they are actually using this idea. Detection algorithm. So suppose that you have some files, file 1, file 2, file 3, and so on and so forth, all the way to file M. And then what the virus protection system would do, it would compute the hash of every of this file. Let's say these are the critical file of your operating system. And then the virus protection software, it tries to protect them against some malicious activity. So f of 2, he computes all the corresponding hashes. And then we would basically store them in some secure location. Store in a secure location. And then once we have them stored in a secure location, if now, let's say F2 is changed to F2 prime, right? And then therefore, because of the secondary, pre-image resistance of this hash function, then the hash of F2 is not going to be equal to hash of F2 prime, right? Otherwise, if somebody can do this change without noticing from the hash function, it means that we violated this property. It means that given some F, you find another F prime such that their hash functions are equal, right? So you can break the hash function. So this is due to second pre-image resistance, right? So it is very interesting. So suppose that you have your major file for your operating system. So when you turn off your laptop, well, of course, somebody can unplug your hard disk drive, change some of those kernel files, install a backdoor, do whatsoever, and then put your hard disk drive back. And then when your operating system is booting up, you will see that the antivirus would say that something has changed. Then it would ask you to take some action. Maybe they wouldn't let the OS to boot, or ask you to check the things, or whatever it is, the decision or the actions that the antivirus would want to take for you. But the point is, the first part, which is the detection, we can easily achieve it with the use of this hash function, cryptographic hash function, because of if you change anything on this file, the resulting hash should be able to show that. So, and that would help us to detect that. The second example that I want to give you is for integrity check. So we can do integrity in transmission. Suppose you have two party A and B that they want to, they want to communicate with each other, and we suppose that they have share a key K. So what they can do is that they can send a message along with the, K concatenated with M, and sometimes they concatenate it again. and to the other party. So what is happening is that only these two parties, A and B, they know this key K, and when they want to transfer this message M, they add key to the beginning and end of that M, concatenate them together, and compute the hash function. So the other party would when it receives it, so he would compute the same hash function based on the M that it receives, and then he would base upon that if the resulting hash value is equal, he would accept the message. Otherwise, he would say that no, I won't accept it. I would reject it because something has happened on the line. Some bits of M has changed, or something doesn't add up. So therefore, this is not the message that A sent to me. And we do that because if this one match, hash of K, M, and K, if you change it to M prime, then, the hash of K XOR with M, this M prime, this should not be equal because of the secondary pre-image resistance property from the hash function. If it, it shouldn't be easy for you to change that message so that the recipient wouldn't able to detect it. We also had in public key crypto, we can convert that one to the public key crypto. So we have A and B again. So A would compute a sigma of this message, saying that hash of M to the D mod N, right? Remember with RSA. And now he can send M and sigma to the B. And B, the hash function that you use there should be pre-image resistance. Otherwise, Eve can find another M prime such that M prime is not equal to M, but hash of M equals to hash of M prime, right? And then if he can do that, then he can say that, hey, A signed this message M prime and sent it to you. And the signature would for sure match because the hash of M equals to hash of M prime. And therefore, he can lower B to accept this message M prime as the correct signature. So now you see that why we said when we designed the cryptographic hash, on the design of RSA digital signature, we said it is very important to make sure that we use a cryptographic hash function. So these are the definition of what we want from a cryptographic hash function. So these two properties happen to be very important. So as I said, looking into the definition of this hash function over here, you could see that there are a lot of hash functions that can match to this description, but very few hash functions are out there that they can satisfy these two strong and important properties. And therefore, a very small family of all hash functions out there can be used for cryptography. So now that we are given this sort of hash function requirements and we understand that why they are important, and so it is the time to sit down together and design the very first hash function. It calls Merkel's meta method. It is a very interesting hash design algorithm. It is a sort of iterative algorithm. Everything starts with a collision resistant compression function. So we were talking about hash functions, but in Merkel, we start with assuming that there is a collision resistant compression function. What does that mean? we are assuming that we have a function that takes some inputs of n plus r bits, and it would compress it into n bits. Okay, so it would just get rid of r bits for some r greater than 0. And then we assume that this f exists, and it is f itself is a collision resistant compression. That means that, you know, all the properties that we said about the hash function, so that you cannot find two messages from the domain that would have the same output, and so on and so forth. So the first challenge that we have in actually designing a hash function is the first one. We always know how to find, no matter what function we work with, they have some restriction on the domain. We don't have any function that can directly take any arbitrary input length. So the magic with the Merkle hash function is that it would use the iteration to just take some function that shrinks only r bits, and then we're going to apply this one iteratively so that we convert this one into a function that can iteratively handle an input of any arbitrary length. So that is the first problem that we want to solve. The second one is that we also need to make sure that we satisfy those two properties. And those two properties are actually nicely coming from this f function. That is a compression, collision resistant compression function. So let's see how does this work. The first thing first that we want to do, so we have some steps that we have to follow for this algorithm to work. So when we receive a message M, we need to chop this message into r bits. So if I want to display this one in a nicer way, I would say this one is going to be my M1, M2, and so on and so forth. I will chop it into, let's say it has MK part, and so this is my M, where every MI over here, the length of MI is actually r bits, right? So that is the first thing that we do. We chop our M into r bits, and every location has r bits. And then there is a new piece that we would add to the end of this that we call it MK plus, MK plus 1. And for that, I lost the box. Okay. So what is that MK plus 1? MK plus 1 is a new, r bit that we added at the end, that one would hold the length of the message itself. So MK plus 1, that block, is equal to length of message M. How many bits do we have in M? And then we concatenate enough zeros so that such that length of MK plus 1 itself becomes R. Okay, so we make sure that every block over here has exactly R bits. Why do we add this length of M to the end of this message? It has some security reason, and in the proof of this this idea, we would see why that is the case, and that is important. Right, so now we have started, we are done with the step 1, we did the padding, and then we also do the step 2. So now we are ready to actually discuss how we would be able to proceed with this algorithm. So I would rather to show with like some graphics and how this algorithm works. So the step number 1 was padding, right? So we get the M, we do padding. We chop it into, I would show that we turn it to M tilde, that is equal to M1, M2, M3, all the way to MK and MK plus 1. We already saw how we do that. Once we are done with the padding, we start with some initial value for the hash, which we call it V0. V0 is always n bit, and then we send this one to our f function. We said that f would take, if you remember over here, we said f would take n plus r bits, and the r bit is coming from here. So this is going to be our m1, right? And this is definitely r bit because we chopped it so that m1 is r bit. And then we get the output, which is n bit again, and our output, we call it v1, right? So we would continue with that, and then we would insert m2 over here and apply the f function, and it would output for us another n bit, which is v2. And again, we continue with this, and so on and so forth, until we get some vk, and then we send our to an f function along with mk plus 1, and then at the end we get the n bit vk plus 1, right? That is the end. And then we define the hash of message m to be vk plus 1, the last output that we get over here. So let's see what happened. So the challenge that we had for a cryptographic hash function was that we need to accept any message with any arbitrary input. But the options that we have out there is some sort of collision resistant compression functions that exist out there, and they satisfy collision resistant and second pre-image resistant, but the problem is that they don't take arbitrary length. They always take n plus some r bits, and then they shrink it down to n bit. So the first challenge we want to solve is that how we can use this idea to turn this function, to design a new function into the case that we can accept any arbitrary length of input. So the Markov would gave this definition, and it works. The way that she suggested was that we basically pad our message, we chop it into r bits, and then we start with always some initial value, and then based on the different values of f or m over here, you see that the output of f would change, and we would do this iteration. It is an iterative hash function, and whatever it returns at the very end after we pass the last block, we define that to be our result of our hash function. And this has simply resolved our first issue that now we can handle any message with any arbitrary input. So now that is given, that is interesting. So then the very next thing that we want to check together is to make sure that the design that we made here, we know that f is collision resistant and second collision pre-image resistant, but after we do this iteration, what happens to the hash function that we build with this idea? Is this going to, is the hash function going to be satisfy those collision resistant and second pre-image resistant as well or not? So here is our theorem. We suppose that f that takes n plus r bits and output n bit is a collision resistant compression function. Then the hash function that is constructed with the above idea is also collision resistant. So we are going to prove it now. To prove this idea, we would start with a contradiction. So I would say by contradiction, assume there exists some m and m prime such that m is not equal to m prime, but the hash of m is equal to hash of m prime, right? By contradiction, we assume that there is such a thing. So the idea that maybe many of you are getting the idea. By contradiction here, what we are trying to show is that we know that we use the Merkle function, compression function, to construct a hash function, if now we show that we have a collusion in our hash function, it means that we can show that there is a collusion in function f. But we assume that function f is collusion resistant, so that is a contradiction, right? So that's how we want to proceed with this proof. So we need to consider two cases for this. So we assume that we have a collusion and in the resulting hash function that we generate with the miracle. How can we show that there is also a collusion for the f function? So we have two cases to follow with. We assume for the first case that the length of m equals to the length of m prime. And for the second case, we assume that their lengths are not the same. Why is it so? Because of our padding, that really matters. So when we take m and we do the padding, we convert it to m1, m2, m3, all the way to mk, and then mk plus 1. And for the case of m prime, we are doing padding. We do m1 prime, m2 prime, m3 prime, so on and so forth, to all the way to mk prime, and then m prime k plus 1, right? So we know that oh, I'm sorry. For the first case, I'm just writing in reverse. Let's do this one is easier. Let's do the case where their length are not the same. So when their length of these two messages are not the same, no matter if whatever blocks are the equal or not, we know that at the last block we add the length of this block and we add padding. So that means that for sure from here, mk plus 1 is not equal to m prime k plus 1, right? That's what we know. Why is it so? Because in the previous page, we said that the last block, we store the length of the input message, right? And add enough padding. We know that the length of m is not equal to the length of m prime, so this for sure should not be equal. But now, since hash of m equals to hash of m prime, what does that mean? That means that if we look into the latest iteration on this hash function, so this is the latest iteration where we get our hash results. The input is vk, and then mk plus 1, and then we get the vk plus 1. So if we look into that, so the vk plus 1 equals to f of vk, the previous input, and mk plus 1. And also this has become equal to the f of v prime k, and then m prime k plus 1, which is v prime k plus 1. So we know that their hash functions are the same. According to the construction of this function, we know that we take the last input output from f function as the result of the hash function. So we know that their hash functions are the same, which means that these blocks are the same. So it means that something was happened within this last f function that we've computed, because these values are for sure different, even though vk's are different if we follow the computation for those two m's, m and m prime. But we know that this mk plus 1 is for sure different, right? So we know that since mk plus 1 is not equal to m prime k plus 1, right? This is what we know for sure. Then it means that these two values, vk concatenate with mk plus 1 and v prime k concatenated with m prime k plus 1 are collusions paired for f, function f. But that is a contradiction, right? So let's review that one more time. We said that we assume that, we construct our function according to the numerical idea. So the first case, number one, is that we find two pairs that they have collusion. In this case, their length happen to not be the same. So if that is the case, we do the padding, even though the intermediate, blocks could be same or not. What we know for sure is that the last blocks are not equal, because that one stores the length of these messages. But since the hash functions of these two messages are the same, so we go back and look at the iteration within that with that f function. So we get our hash result from the last computation. So that means that vk plus 1 and v prime k plus 1. So we know that over here on this computation, mk plus 1 and m prime k plus 1 are not equal, but f function output the same. That means that this input to the f function, vk and mk plus 1 and v prime and m prime k plus 1, are actually those inputs that would let us to find a collusion on f, because their output are the same. And that is a contradiction, because we said that f by default is collusion resistant, but what we show is that after using f to construct a hash function, when we find a collusion in our hash function, that means that there is a collusion in our f function, and that contradicts our assumption that f is a collusion resistant hash function. So therefore, that h, the hash function that we build from f itself, is not a collusion resistant hash function by contradiction. And let's go quickly on the case number 2. On case number 2,
but I don't understand, because here you're just saying that they're the same, and that's why I don't understand how we prove here that there's a contradiction. We just said they were the same.
No, they are not the same. So you see that this is the hash function that we construct, iteratively using function f. Okay,
yeah.
This is the way we design. So what we are showing here is that we know that we are given this function f, and somebody says that there is a proof for function f itself that is collusion resistant. Okay, that is the fact we know. After we found this, we use this f and we create a hash function by this design over here. What we are saying is that our hash function that we created this way is also collusion resistant. Okay. But to prove it, we say we assume that this way that we design it doesn't make it collusion resistant. Then that means that we can find collusions. And once we show that we find a collusion, then we can go back and find a collusion for f function, that because this f causes that collusion. Okay, that is a contradiction, because we said that somebody proved that f is a collusion free, is a collusion resistant hash function. But after we designed this, we are showing that when we find a collusion in our hash function, it means that there is a collusion in f. So that contradicts here, because we assume f is collusion resistant, but we are showing that we can find collusion for f, and that's where it is. There is a contradiction there.
So we're saying, so we're just the number one part that we just did is just showing that the only way that this function will not be will have collusions is if the small f here has collusion.
Yeah.
And we cannot say that.
Yeah, we cannot say that. Yes, exactly.
Okay.
Okay, so that contradicts our assumption. So that is not the case. So in math, we use a lot of this kind of techniques, So this is one of the ways that it helps us in cryptography as well. So this is the case that we discussed, that the collusion happens at the last part of the iteration, right? It just happened over here. But the collusion can also happen somewhere else. And for that, we have to discuss where m, size of m, actually equals to the size of m prime. So how about this case? So for this case, so when we do the padding, so when we convert m to this block, so we get m1, m2, m3 all the way to m k plus 1, I just short it down, and then m prime would go to m1, m2, m3, I'm sorry, prime, all the way to m prime k plus 1. Okay, and then since the length are the same, and on the last block we insert the length of the m, so we know that now mk plus 1 is for sure equals to m prime k plus 1. Unlike the other case that we knew that for sure because the lengths are not the same, this is the thing that we know for sure. These two should be different. Now, no, regardless of the previous block values, we know that the last two blocks must be the same. So now let's do the computation for this guy. Just give me a second. Let me write down the steps for this algorithm. Then we come back and discuss the reasons. So for both of them, we said we start with the f with the same initial value. Then we apply f function m1, and then we get v1, 2. Okay. And then for the second one, we also start with the same initial. So we just pass m prime 1. We get v1 prime now is different. Could be different. F prime 2. Okay, so I wrote down the steps for computing the hash of every of the both of these messages. So we always start with the v0 because this is our initial value no matter what. So for the first one, we follow the computation until we get the vk plus 1. That is the result of the hash function. And then for the second one, we start with the same thing. We would passing different blocks from m prime. And then we follow the computation. What we know at the end is that vk plus 1 equals to vk prime plus 1. Okay, this is what we know from our hash function. So given that, we need to show that there is a collusion in f. Somewhere over here, there is a collusion. So what we are saying is that there is a step I, there is some iteration I that I drew it in red specifically over here. That if you look into this I, because at the end, the result of this hash function are the same. So something would start to change some step is responsible for that. So for that, we have these two conditions. We have VI, the previous one, the previous block for that is either is not the same as V prime I minus 1, or this MI is not the same as M prime I. But the result after that, VI and V prime, should equal to each other. And that is the place that we find the collusion. So what we are saying is that we found the collusion over here, and this collusion does not necessarily come from the last block, because we know that these two guys are the same, but it could actually appear from some I iteration somewhere in the middle, or even at the last one. It doesn't matter. But we want to just be more generic. So we are saying that the collusion happened at some point in the past, that if you look at the input to the hash to the f function, at some point there is a collusion because these outputs are the same. So what causes to that is that either these two things are not the same and these two guys are the same, or vice versa, that MI could be different, and also these two guys should be the same. So that should be the cause of that, if that ever happened. And once we find that iteration I, then we say that f of Vi minus 1 concatenated with Mi equal to f of V prime I minus 1 concatenated with M prime I, right, is a collision pair for f. But again, that is a contradiction, because we said that f is collision resistant hash function. So given 1 and 2, I would say that we conclude that the hash function that we design in this way, or hash function, is collision resistant. Okay, so let me go through the steps one more time. So we start with the fact that f, somebody gave it to us, and it says that this f is a collision resistant hash function. We design a hash function using that f, and after we design our hash function, we show that we, whenever we find a collusion in our hash function, and it's easy to find, and then we can trace back based on our design and give exactly where that collusion happened in f function, a small f. But we know that by design, somebody gave us that f, and it said that that is a collusion resistant hash function. And that means that the design that we made is collusion resistant, because once somebody find a collusion in our hash function, they can also find that collusion in our f function. So the only thing we had to show was that, okay, so given that there could be a collusion in our hash function, where that collusion happens on f function. So we consider two cases. In the first one, the collusion we would find at the last iteration. For the second one, it could also happen at the last iteration, but we are not restricted. It could happen on some previous steps. So we said that there is a I that, either these inputs are not the same, but the outputs are the same, or the MIs are different. And then one of these conditions, these two could be the same or not. But no matter what, the output of this f function at this step has been the same, and that's caused this collusion. So for both these cases, we kind of use a trick, right? We didn't really prove directly if this f function is collusion resistant, but we leverage the fact that f is a collusion resistant compression function, and we use that to also show that our function cannot be collusion resistant, right? Otherwise, f is not collusion resistant. Yeah, okay. Let's get some break time, and we come back at 10 to continue.